In September of 2019, a team at Heriot-Watt University in Edinburgh ran an experiment that should have made front-page news in every country on Earth. It did not. You almost certainly never heard about it. And the reason you never heard about it is the same reason you are going to want to sit down for this. The experiment was led by Massimiliano Proietti. His team built an apparatus using 6 entangled photons, 64 different measurement configurations, and ran the whole thing for 360 hours straight. They collected 1,794 coincidence events. That is a very specific number, and I want you to remember it. Because what those 1,794 events revealed is something that cuts directly against one of the most basic assumptions you have ever made about the world. The assumption is this: you believe that when something happens, it happens. A coin lands heads, a particle hits a detector, a tree falls in the forest. You believe that these events are facts, not opinions, not perspectives. Facts. Things that occurred definitively, regardless of who was watching. Proietti's experiment tested whether that belief is true, whether events that happen in front of one observer are the same events from the perspective of another observer, whether reality is the same for everyone. The result, published in Science Advances, was a Bell-type inequality violated by 5 standard deviations. In physics, 5 sigma is the threshold for discovery. It is the same bar that had to be cleared to confirm the Higgs boson. And what it confirmed in this case is that if you accept 2 things physics has accepted for a century, locality and free choice, then you have to give up a 3rd thing: observer-independent facts. The idea that what happened, happened, period. That is not a thought experiment, that is not philosophy, that is a laboratory result from a major university published in a peer-reviewed journal. And the implication, stated carefully but unmistakably in the paper itself, is that different observers can experience genuinely different, irreconcilable realities. Not different interpretations of the same reality, different realities. If you are thinking that sounds like the kind of thing a New Age YouTube channel would say right before trying to sell you a crystal, I understand the instinct. That is exactly what makes this so uncomfortable. Because the argument that consciousness is involved in creating reality did not come from mystics. It came from the single most important mathematician of the 20th century, and it has been sitting in the foundations of physics unresolved since 1932. John von Neumann was not a physicist who dabbled in math. He was possibly the most formidable intellect the 20th century produced. He co-invented game theory. He designed the architecture that every computer on Earth still uses. He was one of the key minds behind the Manhattan Project. And in 1932, he published a book called Mathematical Foundations of Quantum Mechanics that did something nobody talks about in popular science. He proved, rigorously mathematically, that the equations of quantum mechanics contain a problem that has never been solved. The problem is this: quantum mechanics has 2 rules, and they contradict each other. Rule 1 says that when you are not measuring a quantum system, it evolves smoothly and predictably according to the Schrödinger equation. Rule 2 says that when you do measure it, the system undergoes an abrupt, irreversible change called collapse. It snaps from a haze of possibilities into a single definite outcome. The wave function, which described all those possibilities, is gone. One result remains. Here is the question von Neumann asked that nobody could answer then and nobody can answer now. Where exactly does that collapse happen? If a particle hits a detector, is the collapse at the detector? But the detector is made of atoms, and atoms obey quantum mechanics. So the detector should be in a superposition too. What if a computer reads the detector output? Same problem. The computer is physical. It should also enter a superposition. What about when a human reads the computer screen? Von Neumann proved that you can push this boundary, this line between the quantum world and the definite world, anywhere you want along the chain, from the particle to the detector, to the computer, to the human eye, to the neurons in the human brain. And the final statistical predictions of quantum mechanics do not change. The math works no matter where you draw the line. You can push it all the way to what he called the abstract ego, the conscious mind. He did not say consciousness causes collapse. That is an important distinction and one that gets lost in almost every retelling. What he said is that the formalism permits it. The equations do not tell you where to draw the line. They leave a hole, and that hole has been open for 93 years. It was two other physicists who walked through it. The first was Fritz London, working with Edmund Bauer. In 1939, they published a 51-page monograph in Paris, arguing that what cuts the chain, what determines where quantum possibility becomes definite reality, is the observer's faculty of introspection, the ability to immediately know your own state. Consciousness, in their formulation, was the thing that broke the infinite regress, the thing that said, here is where possibility ends and fact begins. The second was Eugene Wigner, and to understand why his contributions shattered things the way it did, you need to know something about who he was, because Wigner and von Neumann were not colleagues who happened to work in the same field. They were childhood friends. Both of them grew up in Budapest in the early 1900s. Both attended the Lutheran Gymnasium on Faysor Street, one of the most remarkable schools in the history of science, the same school that produced Edward Teller, Leo Szilard, and John Hassani. Von Neumann was 1 year behind Wigner. Their math teacher, Laszlo Ratz, recognized von Neumann as a once-in-a-generation mind and arranged private tutoring from university professors while the boy was still a teenager. Wigner walked home with von Neumann after school, listening as he explained the wonders of advanced mathematics. Years later, Wigner would say, "He was a much better mathematician than I was and a better scientist, but I knew more physics." Both came from Jewish families in a city that would soon become very dangerous for Jewish families. In 1930, Princeton recruited them simultaneously at 7 times Wigner's European salary. They anglicized their names from Gino and Janos to Eugene and John. They built careers on opposite sides of the same building. Von Neumann invented the computer and helped design the hydrogen bomb. Wigner won the Nobel Prize in Physics in 1963 for his work on symmetry principles in nuclear physics. And in 1961, Wigner published a paper that detonated a quiet bomb in the foundations of his field. The paper was called Remarks on the Mind-Body Question, and it appeared in a collection called The Scientist Speculates. In it, Wigner took von Neumann's open question and drove straight through it. He wrote, and these are his exact words because they matter, "It was not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to the consciousness." He wrote, "It is the entering of an impression into our consciousness which alters the wave function because it modifies our appraisal of the probabilities for different impressions which we expect to receive in the future. It is at this point that the consciousness enters the theory unavoidably and unalterably." He wrote, "The being with a consciousness must have a different role in quantum mechanics than the inanimate measuring device." This was not a philosopher speculating, this was a Nobel laureate in physics, one of the greatest mathematical minds alive, saying that consciousness enters quantum mechanics and cannot be removed. Then he proposed a thought experiment that made the problem impossible to avoid. Imagine, Wigner said, that a friend of yours performs a measurement on a quantum system inside a sealed laboratory. From the friend's perspective, the measurement happens normally. They see a definite result. But from your perspective outside the lab, quantum mechanics says the friend and the system should be in a joint superposition. The friend is simultaneously someone who saw result A and someone who saw result B, until you open the door and ask, at which point the friend cheerfully reports that they always saw one definite outcome all along. Both descriptions cannot be right. Either the friend experienced a definite outcome inside the lab, which means quantum mechanics breaks down when conscious beings are involved, or the friend really was in a superposition until you looked, which means their subjective experience of having seen a definite result was somehow not real until a second consciousness confirmed it. For decades, this was treated as an interesting philosophical curiosity, the kind of thing you discuss at conferences after the serious talks are done, maybe over drinks, probably not in front of anyone who controls your tenure case. Then Proietti's team actually tested it. And the reason that should disturb you is not just the result itself. It is what happened next. Or rather, what did not happen next. Because the result confirmed quantum mechanics. The friend's reality and Wigner's reality genuinely conflict. They are not two perspectives on one event. They are two irreconcilable descriptions of what occurred, both supported by the data. And the world did not react. No reckoning. No public conversation about what it means that the most basic assumption underlying all of science, that facts are facts, has been experimentally challenged at 5 sigma. MIT Technology Review ran a piece. A handful of philosophy blogs discussed the implications, and then everyone moved on, as if the ground beneath everything had not just developed a crack. And here is the part I need you to hear. That experiment was just the beginning, because every attempt to patch this crack, every attempt to remove consciousness from the equations, every attempt to explain away what von Neumann identified in 1932 has failed. One by one, over the course of almost a century, the sharpest minds in the history of science have tried to solve this problem. And what they discovered, repeatedly, is that the problem is worse than they thought. What follows is not a question about whether consciousness creates reality. That is the question you think you came here for. The real question is darker. The real question is why physics cannot get rid of consciousness no matter how hard it tries. And what it means that every serious attempt to do so has not just failed, but has made consciousness more central, more necessary, more fundamental than it was before the attempt began. Every path leads back to the same place. And what is waiting there is something the people who should be able to explain it either cannot or will not say out loud. But to see why that should frighten you, you first need to see the wreckage. You need to see what happened to the people who tried to solve this. Because the history of this problem is not a story of gradual progress toward understanding, it is a graveyard of failed solutions. And the bodies in it belong to some of the greatest minds who ever lived. The first solution was supposed to be definitive. It was supposed to bury Wigner's question forever, seal the crack von Neumann found, and restore a universe where facts are facts and consciousness is just something brains do. It was called decoherence, and for about 2 decades, a lot of very smart physicists believed it worked. To understand why it does not, and why its failure matters, you need to understand what the actual problem looks like from the inside. Not the version you get from popular science, where particles are magically in 2 places at once and cats are alive and dead. The real version, the one that keeps physicists awake. When you fire a single photon at a barrier with 2 slits, something happens on the other side that should be impossible. The photon does not go through one slit or the other. It goes through both. You know this because on the detector screen behind the barrier, you do not see 2 bright spots. You see an interference pattern, alternating bands of light and dark, the signature of 2 waves overlapping, peaks reinforcing peaks, peaks cancelling troughs. The photon interfered with itself, which means it traveled through both slits simultaneously. That already defies everything you know about how objects behave. But here is where it gets worse. If you put a detector at one of the slits, something you can use to determine which path the photon took, the interference pattern vanishes instantly. The photon behaves like a particle again, going through one slit, producing one spot, The act of determining which path it took destroyed the superposition. The act of looking changed what happened. That is the double-slit experiment, and it has been repeated tens of thousands of times with photons, electrons, atoms, and molecules containing over 800 atoms. The result never changes. When you do not look, the quantum system exists in a superposition of possibilities. When you look, it collapses into one. Now here is where I need to correct something, because there is a misconception about this that has probably been living in your head for years. When people say observer, they usually picture a human being watching something, a conscious mind choosing to look. And that is not what the physics community officially means by the word. In standard physics, an observer is any physical interaction that extracts information. A Geiger counter clicking, a photon bouncing off an electron, a molecule bumping into a surface. No consciousness required. Werner Heisenberg himself wrote that the observer has only the function of registering decisions, and it does not matter whether the observer is an apparatus or a human being. That sounds like it settles the question. Consciousness is irrelevant. The collapse happens whenever any physical interaction extracts information. Problem solved. But it is not solved because of the von Neumann chain. Remember what he proved. The line between quantum and classical, between possibility and fact, can be drawn anywhere and the math does not care. A Geiger counter is made of atoms. Those atoms obey quantum mechanics. So why does the Geiger counter get to be classical? Why does the Geiger counter get to collapse the wave function when the Geiger counter itself should, according to quantum mechanics, be in a superposition right alongside the particle it is measuring? This is the measurement problem, and the answer most physicists gave for the second half of the 20th century was decoherence. Decoherence works like this. A quantum system in a superposition is not actually isolated. It interacts with its environment, with air molecules, photons, vibrations, the whole thermodynamic mess of the macroscopic world. And those interactions cause the quantum system to become entangled with billions of environmental particles. The interference between the different branches of the superposition gets smeared out, diluted across so many particles that it becomes undetectable. The system looks classical. It looks like it collapsed. Problem solved. And for a while that was convincing. The physicist who developed this framework most rigorously was H. Dieter Zeh, starting with a 1970 paper, later extended by Wojciech Zurek at Los Alamos, into a comprehensive theory of decoherence and the quantum to classical transition. Wigner himself was persuaded. By 1982, he had abandoned his own consciousness argument, calling it a form of solipsism, largely because Zeh's decoherence seemed to make consciousness unnecessary. But decoherence has a problem, and the problem is fatal. Decoherence explains why quantum superpositions become undetectable at the macroscopic level. It explains why you do not see cats that are both alive and dead. It explains the appearance of collapse, but it does not explain collapse itself. Decoherence converts quantum probabilities into classical probabilities. It takes a quantum state where the cat is in a superposition of alive and dead and turns it into a state that behaves like a classical mixture, where the cat is definitely alive or definitely dead, and you just do not know which until you look. But it does not tell you why you get one specific outcome. As Sabine Hossenfelder has put it, decoherence converts quantum probabilities to classical probabilities, but it does not tell you how a particle ends up in one and only one possible measurement outcome. Think of it this way. Before decoherence, you have a coin spinning in the air. After decoherence, you have a coin that has already landed but is covered by a cup. Heads or tails, definitely one or the other, you just cannot see which. But the question of why it landed heads instead of tails, the question of what selected that particular outcome from among all the possibilities, is completely unanswered, decoherence swept the mess under the rug. The mess is still there. This matters because the measurement problem is not a quirk. It is not some marginal technicality at the edges of physics. It is the question of why the world you experience is definite at all, why you see one thing happen instead of all possible things happening simultaneously. And decoherence, the thing you were probably told solved this, does not answer that question. It just makes it harder to notice that the question was never answered. And that is where things take a turn that almost nobody saw coming. Because the person who tried the hardest, who went the furthest, who sacrificed the most to remove consciousness from quantum mechanics, was a young graduate student at Princeton in the 1950s. His solution was more radical than anything Wigner or von Neumann had proposed. He did not just redraw the line between quantum and classical. He erased the line entirely. He said the wave function never collapses at all. Every possibility is real. Every measurement splits the entire universe into parallel branches. One branch for every possible outcome, extending backwards and forward in time. Forever. His name was Hugh Everett III. His idea is called the many worlds interpretation. And his story is the single most tragic cautionary tale in the history of physics. Everett was brilliant and strange from the beginning. At the age of 12, he wrote a letter to Albert Einstein asking whether something random or unifying held the universe together. Einstein wrote back, telling the boy there is no such thing as an irresistible force and an immovable body, but there seems to be a very stubborn boy who has forced his way victoriously through strange difficulties created by himself for this purpose. You need to hold that letter in your mind for what comes later. As a graduate student at Princeton, Everett studied under John Archibald Wheeler, who was at that time one of the most influential figures in physics. Wheeler had worked with Niels Bohr. He had mentored Richard Feynman. He would go on to coin the term black hole. And he gave Everett a problem that seemed simple on its surface. Apply quantum mechanics to the universe as a whole. Write down a wave function for everything. The problem Everett discovered was that if you take quantum mechanics seriously, if you refuse to add collapse as a special rule that happens at some arbitrary boundary, then the wave function of the universe never collapses. It just keeps branching. When you measure a particle that is in a superposition of spin up and spin down, the universe splits. In one branch, you see spin up. In another, you see spin down. Both branches are equally real. Both versions of you exist. The wave function keeps evolving smoothly, exactly as the Schrödinger equation says it should, with no special rule for measurement, no magical collapse, and critically, no role for consciousness whatsoever. This was the supreme irony. Wigner, Everett's senior colleague at Princeton, was arguing that consciousness is essential to quantum mechanics. Everett, working in the next building, was arguing the exact opposite. His entire thesis was designed to make consciousness irrelevant, to show that you do not need a conscious observer to collapse the wave function, because the wave function never collapses, it just branches. In 1957, Everett published his thesis. Wheeler had shepherded it through, edited it down from a long version to a short, one to appease Bohr and the Copenhagen establishment. Wheeler believed in the work, but was terrified of offending his mentor, and what happened next defined not just Everett's career, but the entire trajectory of this question. In 1959, Everett traveled to Copenhagen to present his ideas to Bohr and his circle. It was a disaster. Leon Rosenfeld, Bohr's lieutenant, later described Everett as undescribably stupid and incapable of understanding the simplest things in quantum mechanics. Everett called it a hell and said the meeting was doomed from the beginning. Bohr would not engage. The Copenhagen Circle dismissed him with the particular contempt that powerful people reserve for those who threaten the foundation of their authority. Everett never published another paper in physics. He left academia entirely and went to work at the Pentagon for the Weapons Systems Evaluation Group. He co-founded Lambda Corporation in 1964 and DBS Corporation in 1973. Defense contractors. He spent the rest of his career calculating nuclear megadeath scenarios, estimating how many hundreds of millions of people would die in various configurations of thermonuclear war. He chain-smoked 3 packs a day. He drank heavily. He became grossly overweight. He never exercised. He never saw a doctor. His son Mark would later describe him as a lump of furniture sitting at the dining room table. He was an atheist and a self-described solipsist, a man who had spent his youth trying to remove consciousness from the universe and ended up unable to connect with the conscious beings in his own home. On July 19, 1982, Hugh Everett died in his bed of a heart attack. He was 51 years old. His teenage son Mark found the body. Mark would later say, "I did not know how to feel about the fact that my father just died. I did not really have any relationship with him." Everett had requested that his ashes be thrown in the trash. His wife eventually honored that request. 1 month before Everett died, his daughter Elizabeth had made her first suicide attempt. In 1996, she succeeded. She left a note. It said, "Please burn me and do not file me. Please sprinkle me in some nice body of water or the garbage. Maybe that way I will end up in the correct parallel universe to meet up with Daddy." Think about what that sentence means. A daughter trying to use her father's physics, the physics he invented to escape the consciousness problem, to reach him across the boundary of death. Trying to navigate the many worlds interpretation to find the branch where she and her father could finally connect. Mark Oliver Everett went on to become the frontman of the rock band Eels. He had been unaware of his father's scientific significance until after his death. A BBC documentary called Parallel Worlds, Parallel Lives followed Mark as he retraced his father's intellectual journey, meeting the physicists who now celebrated the work that had been rejected in his father's lifetime. And here is what makes Everett's sacrifice especially bitter. Many worlds does not actually solve the problem it was designed to solve. It removes collapse. It removes the need for a special rule about measurement. But it has its own version of the consciousness problem that almost nobody discusses publicly. The question is this: in many worlds, when the universe branches, why do you experience only one branch? All branches are equally real. All versions of you exist. The wave function says so. But you, the you reading this, the you with your specific memories and your specific perspective, only experience one outcome. Why? What selects your branch? What makes you the version of you that saw spin up instead of spin down? The standard answer is the Bohm rule, the mathematical formula that gives the probability of each outcome. But in many worlds, every outcome happens with certainty. So where do probabilities come from? Why do the Bohm rule probabilities match what we actually observe? This is called the probability problem in many worlds, and it has consumed hundreds of papers and decades of work by people like David Deutsch, David Wallace, and Lev Weidman, without producing a consensus. And lurking beneath the probability problem is something deeper, something almost nobody wants to say plainly. The question of why you experience one branch is a question about consciousness. It is a question about what it means to have a perspective, to be one observer among the infinite copies of yourself that many worlds says exist. Everett split the entire universe to avoid the consciousness problem. He paid for it with his career, his family, and arguably his life. And the consciousness problem is still there, hiding inside his own theory, waiting. That is 2 failed attempts to remove consciousness from physics. Decoherence failed because it explains the appearance of collapse, but not collapse itself. Many worlds failed because it eliminates collapse but cannot explain why you experience one outcome. Both approaches were supposed to make consciousness irrelevant. Both ended up presupposing something about consciousness that they cannot explain. But there was a third approach, and unlike the first two, This one did not try to remove the observer from the picture. It tried to make the observer the entire picture. It was proposed by a man who had spent his career thinking about what it means to observe, and who arrived at a conclusion so radical that even his admirers were not sure what to do with it. His name was John Archibald Wheeler, and the idea he put forward in the last phase of his career may be the most unsettling proposal in the history of physics. Wheeler was Everett's thesis advisor. He had mentored Feynman. He had worked alongside Bohr in Copenhagen. He was the man who coined the term black hole at a conference in 1967, a phrase so perfect that it changed how an entire civilization thinks about gravity. He named wormholes. He named quantum foam. He was, by the middle of the 20th century, one of the most dominant and respected figures in all of physics. And then, starting around 1978, he began saying things that made his colleagues very uncomfortable. It started with the delayed choice experiment. Wheeler proposed a variation of the double slit experiment that cuts directly at the question of whether the past is fixed. In the standard double slit setup, you decide before the photon arrives whether to measure which slit it goes through or to let it pass unmeasured and produce an interference pattern. Wheeler asked, what if you wait? What if you let the photon pass through the slits, travel toward the detector, and only then, after it has already committed to one behavior or the other, make your choice about how to measure it? Quantum mechanics predicts that your delayed choice still determines the result. If you choose to measure path information after the photon has already passed through the slits, the interference pattern disappears. If you choose not to, the pattern appears. The photon seems to retroactively adjust its behavior to match a decision that had not yet been made when it passed through the slits. This was experimentally confirmed in 2007 by Vincent Jacques and his colleagues, published in Science. They used true single photons with space-like separated random choices, meaning the decision about how to measure was made so late and so far away that not even light could have carried the information back to the photon in time. The result was unambiguous. Closed configuration, interference visibility at 94%. Open configuration, path determined with less than 1% error. The delayed choice works exactly as Wheeler predicted. In 2017 and 2018, the experiment was extended to thousands of kilometers using satellite ground interferometry. And in 2018, an MIT and Vienna team used the ultimate delayed choice. They pointed their detectors at quasars using light that had been traveling for 7.8 and 12.2 billion years, and used the color of that ancient light to randomly determine the measurement settings. Even with the choice dictated by photons emitted before the Earth existed, the quantum predictions held. The present measurement determined what happened in the past. Think about what that means. Not in an abstract, theoretical way, in a personal way. A choice you make now, in this room, at this moment, affects what a photon did billions of years before you were born. Your measurement does not reveal a pre-existing fact about the photon. It participates in creating that fact. The past is not fixed. The past is responsive to the present, and it is responsive specifically to acts of observation. Wheeler knew exactly what this implied, and unlike many of his peers, he did not flinch from it. In 1989, at a conference at the Santa Fe Institute, he introduced a phrase that would define the final phase of his career: it from bit. Otherwise put, he said, every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no questions, binary choices, bits. All things physical are information theoretic in origin, and this is a participatory universe. That word, participatory. Wheeler chose it deliberately. He did not mean the universe is interactive in the way a video game is interactive. He meant something much more radical. He meant the universe does not fully exist until it is observed. That observation is not a passive act of recording what is already there, but an active act of bringing reality into being. He drew a diagram, his famous U-shaped figure, showing the universe as a capital letter U, with one end being the Big Bang, and the other end being an eye, the eye of an observer, looking back at the beginning. The universe observing itself into existence. A self-excited circuit, as he called it, where the observer and the observed are not separate things but aspects of a single system that brings itself into being through acts of measurement. No phenomenon is a real phenomenon until it is an observed phenomenon, Wheeler wrote. We are participants in bringing into being not only the near and here, but the far away and long ago. The universe does not exist out there, independent of us. We are inescapably involved in bringing about that which appears to be happening. He used an analogy that is worth sitting with. Imagine, he said, playing 20 questions, the game where one person thinks of a word and the others ask yes or no questions to guess it. Now imagine a variation where nobody has chosen a word in advance. Each person only decides their answer after the question is asked, with the sole constraint that their answer must be consistent with all previous answers. By the end of the game, a word emerges that was not in the room when the game started. It was not pre-existing. It was created collectively by the process of asking and answering. Wheeler said the universe works the same way. The electron before measurement is neither wave nor particle. It is not anything definite. The act of measurement participates in creating what it finds. This was not New Age mysticism. This was the man who had worked with Bohr, mentored Feynman, and coined black hole, saying at the end of a 60-year career in physics that reality requires participation to exist. But Wheeler's participatory universe had a problem. A serious one. If reality is created by observation, by acts of measurement, by what Wheeler called apparatus-elicited answers to yes or no questions, then what is doing the observing? What is asking the questions? Wheeler talked about apparatus, about measurements, about information. But apparatus is made of atoms. Atoms obey quantum mechanics. We are right back in the von Neumann chain. The question loops back to the same place it always loops back to. What, at the very bottom of it all, is the thing that observes? Wheeler never answered that question directly, but one of his students did. Or rather, one of his students dissolved the question entirely in a way that is either the most brilliant move in the history of physics or the most disturbing. Christopher Fuchs was a quantum information theorist who had trained under Wheeler and absorbed his participatory worldview. Starting in the early 2000s, working with Carlton Caves and Rudiger Schack, Fuchs developed an interpretation of quantum mechanics that took Wheeler's insight to its logical endpoint. They called it Cubism. It stands for quantum Bayesianism, though Fuchs later said the name was chosen partly because it sounds like cubism, and the whole theory is about perspective. Cubism makes a single devastating move. It says the wave function is not a description of reality, it is a description of an agent's beliefs about reality. Your beliefs. Specifically, your subjective degrees of expectation about what you will experience when you interact with the world. When you write down a quantum state, you are not describing what a particle is doing. You are encoding what you personally expect to happen if you measure it. Collapse in cubism is not a physical event. Nothing breaks, nothing snaps from many to one. Collapse is Bayesian updating. It is you changing your beliefs in response to a new experience. Before the measurement, you had certain expectations. After the measurement, you experienced a specific outcome, and you update your beliefs accordingly. The Bohm rule, the mathematical formula that gives the probabilities in quantum mechanics, is not a law of nature in cubism. It is a normative rule, a rule about how a rational agent should set their expectations, like a rule about how to bet, not a rule about how dice work. This dissolves the measurement problem entirely. There is no collapse event that needs to happen at some point in the von Neumann chain, because there is no collapse. There is no wave function of the universe, because wave functions belong to agents, not to the universe. There is no Wigner's friend paradox, because Wigner has his beliefs and his friend has different beliefs, and there is nothing contradictory about two agents having different subjective expectations. But here is where it gets uncomfortable. Fuchs himself says things like this: quantum mechanics is a law of thought, and this. When an agent reaches out and touches the world, a little moment of creation occurs in response. And this, there is no one way the world is. It is still in creation, still being hammered out. In 2017, Fuchs coined a term for what cubism implies about the nature of reality. He called it participatory realism, explicitly connecting his work to Wheeler's vision. He wrote, "Rather than relinquishing the idea of reality, these views are saying that reality is more than any third-person perspective can capture." Do you see what happened? Cubism dissolves the measurement problem. It removes collapse, removes the paradoxes, removes the contradictions. But it does so by placing the experiencing agent at the absolute center of physics, not as an optional extra, not as an observer who passively records what is already there, as a participant whose experiences are the only things quantum mechanics actually talks about. The wave function is not about the world, it is about what the world does to you, and that you, that experiencing subject, is something cubism accepts as given, as primitive, as the starting point of the whole theory. Fuchs does not call cubism a consciousness interpretation. He is careful about this. He says cubism is about agents, about actions and experiences, not about consciousness per se. But the critics have noticed what is going on. Travis Norson at Smith College calls cubism FAPP, solipsism, meaning for all practical purposes, it is indistinguishable from saying only my experience is real. Tim Maudlin at NYU objects that cubism evades Bell's theorem, the most important result in the foundations of physics, by simply denying that quantum states describe reality. If nothing is real until an agent experiences it, then Bell's theorem has nothing to bite into. And David Mermin, the Cornell physicist, who became cubism's most articulate convert, wrote a paper called "Cubism Puts the Scientist Back into Science," published in Nature in 2014. The title tells you everything. The scientist, the conscious, experiencing, believing human being, placed not at the periphery of physics, but at its center. David Mermin is worth pausing on for a moment. He is the physicist who was told at Harvard, early in his career, that he would never get a PhD if he allowed himself to be distracted by such frivolities as asking what quantum mechanics actually means. Foundations work, the kind of work that asks what measurement is and what the wave function represents, and whether consciousness matters, was career poison for decades. You could build a career measuring things. You could not build a career asking what measurement is. Mermin spent decades playing by the rules, becoming famous for his work on quasicrystals and solid-state physics, and only after achieving unassailable prominence did he turn, publicly and enthusiastically, to the foundational questions that had haunted him since graduate school. His conversion to cubism was not a casual endorsement. It was a declaration from one of the most respected physicists in America that the consciousness problem in quantum mechanics is not a problem that can be dismissed. It is, in his view, the problem. Here is where the score stands after 3 attempts. Decoherence tried to make consciousness irrelevant by showing that quantum behavior becomes invisible at large scales. It failed because it cannot explain why one outcome occurs instead of all possible outcomes. Many worlds tried to make consciousness irrelevant by saying all outcomes occur in parallel branches. It failed because it cannot explain why you experience one branch or where the probabilities come from. And Cubism tried to dissolve the problem entirely by making quantum mechanics about the beliefs of agents rather than the properties of objects. It succeeded in dissolving the paradoxes, but at the cost of placing the experiencing agent at the center of physics, which is precisely the thing all three approaches were supposed to avoid. Each attempt to remove consciousness from the picture ended up making it more central. And if Cubism is right, if the best dissolution of the measurement problem is to accept that physics describes what reality does to minds, then the obvious next question is the one that should keep you awake tonight. What is a mind? What is consciousness? And if physics depends on it, if reality itself is participatory in the way Wheeler and Fuchs claim, then what does it mean that we have absolutely no idea what consciousness is? That question has a name. It was given that name in 1994 at a conference in Tucson, Arizona, by a young philosopher who walked onto a stage and said something that the entire field of neuroscience is still trying to recover from. His name was David Chalmers, and the name he gave the question is the hard problem of consciousness. But here is what nobody tells you about the hard problem. It is not just a problem for neuroscience. It is not just a puzzle about brains and neurons and information processing. The hard problem of consciousness is entangled with the measurement problem of quantum mechanics in a way that researchers in both fields would rather not acknowledge, because if you follow the thread from von Neumann through Wigner, through Wheeler through Fuchs, you arrive at a place where the two deepest unsolved problems in all of science are not two problems at all. They are the same problem, seen from different angles. And the people whose job it is to solve it have spent 25 years and $20 million trying. And what they found is that neither problem is getting easier. Both are getting worse. The scene was the first toward a Science of Consciousness conference, Tucson, Arizona, April 1994. The conference was itself something new, a gathering that took the question of consciousness seriously as a scientific problem rather than a philosophical curiosity best left to poets and mystics. David Chalmers was 27 years old. He had a ponytail, leather pants, and a background in mathematics and philosophy from the University of Adelaide and Indiana University. He walked onto a stage filled with neuroscientists, many of whom believed they were on the verge of cracking the neural code of consciousness, and he told them they were solving the wrong problem. He drew a distinction that hit like a blade. On one side, the easy problems of consciousness. These are the problems about mechanisms. How does the brain discriminate between stimuli? How does it integrate information from different senses? How does it produce verbal reports about internal states? How does attention work? How does the difference between wakefulness and sleep operate at the neural level? Chalmers called these easy, not because they are simple, but because they are the kind of problems that science knows how to approach. Find the mechanism, trace the circuit, map the correlation, and in principle you have your answer. They are engineering problems, however fiendishly complex. On the other side, the hard problem, why is any of this processing accompanied by subjective experience? Why does it feel like something to see the color red? Why does the scent of coffee produce an inner sensation and not just a chemical cascade that produces behavior? You can describe every neuron in the visual cortex firing when a person looks at a sunset. You can map the exact pattern of activation. You can explain how the information flows and how the behavioral response is generated. You have left nothing out of the physical description. And yet you have not explained the most obvious fact about the experience, which is that there is something it is like to have it. There is an inner movie playing, a felt quality, what philosophers call qualia. Chalmers put it like this: structure and dynamics adds up only to more structure and dynamics. No matter how much physical detail you pile on, you are describing the mechanism by which information is processed. You are not describing why that processing is accompanied by experience. A thermostat processes information about temperature. It discriminates, it responds, it adjusts. But presumably there is nothing it is like to be a thermostat. Presumably the processing happens in the dark, with nobody home. So what is different about a brain? What makes the processing light up with awareness? And how could any amount of physical description, no matter how complete, explain that transition from dark processing to felt experience? This was not a claim that consciousness is magic or that it lies beyond science forever. Chalmers was making a structural argument about what physical explanation can and cannot do. Physics describes structure and dynamics. It tells you what things are made of and how those things behave. But consciousness is not a structure, and it is not a dynamic. It is the felt quality of structures and dynamics, and you cannot get from one to the other without something extra, some new principle, some new law, something physics does not currently have. Chalmers proposed what he called the zombie argument. Imagine a being physically identical to you, atom for atom, neuron for neuron. It behaves exactly like you. It talks, it laughs, it claims to have experiences. But there is nobody home. The lights are off inside. There is no subjective experience whatsoever. Chalmers argued that this scenario is conceivable, which means it is logically possible, which means consciousness is not logically entailed by the physical facts. You can have all the physics and still not have consciousness. Therefore, consciousness is something over and above the physical. Daniel Dennett at Tufts has spent decades arguing this is nonsense, that the zombie concept is incoherent, that once you have all the functional properties of a brain, you necessarily have consciousness. But even Dennett's allies have struggled to explain how precisely the transition from mechanism to experience works. The hard problem has not been solved. It has barely been dented, and here is where it connects to everything we have been discussing. If consciousness is not just a byproduct of physical processing, if it is something that physics cannot currently explain, then the measurement problem takes on a completely different character, because the measurement problem asks where collapse happens, and every answer that says collapse happens at such and such a physical threshold, at decoherence, at gravitational self-energy, at some objective scale, still has to answer why that threshold produces definite experience. Why crossing the threshold means somebody is home to see the result. The hard problem and the measurement problem are not two separate riddles that happen to coexist. They are two faces of the same coin, and you cannot solve one without confronting the other. Chalmers himself saw this in The Conscious Mind, published in 1996. He proposed that the fundamental stuff of the universe is information with two aspects, a phenomenal aspect and a physical aspect. Every piece of information has an inner face and an outer face. Physics describes the outer face. Consciousness is the inner face. This leads naturally, as Chalmers acknowledged, to Panpsychism, the view that consciousness is not something that emerges at a certain level of complexity, but something that exists at every level of physical reality, even electrons, even photons, even the vacuum of space. We will come back to that, because right now I need you to understand what happened when science decided to throw money at this problem. Serious money. Institutional money. The kind of money that is supposed to buy answers. In 2003, the John Templeton World Charity Foundation committed $20 million to an adversarial collaboration designed to test competing theories of consciousness in the most rigorous way possible. The project was called Cogitate. It was led by Lucia Meloni at the Max Planck Institute and NYU. 256 participants were studied using fMRI, magnetoencephalography, and intracranial electroencephalography across 6 independent laboratories. The two theories being tested were integrated information theory, developed by Giulio Tononi at the University of Wisconsin, and global neuronal workspace theory championed by Stanislas Dehaene. Integrated information theory, or IIT, is the most mathematically rigorous theory of consciousness anyone has ever built. Tononi started developing it in 2004. The central idea is that consciousness corresponds to a quantity called phi, which measures integrated information. Specifically, phi measures how much information a system generates as a whole, above and beyond what its individual parts generate independently. If a system has phi greater than 0, it has some degree of consciousness. If phi equals 0, the system has no consciousness at all. More phi means more consciousness. IIT makes specific predictions. It predicts that consciousness correlates with sustained activity in the posterior cortex of the brain, not the prefrontal cortex. It predicts that simple feed-forward networks, no matter how complex, have 0 phi and therefore 0 consciousness. And it predicts, with an implication that has made many people very uncomfortable, that any system with integrated information above 0 is conscious to some degree. A logic gate, a photodiode, an atom. This is panpsychism derived from mathematics, not assumed as a premise but generated as a prediction of the theory. Global neuronal workspace theory predicts the opposite in important ways. It predicts that consciousness arises when information is broadcast across the brain through ignition events, sudden bursts of activity in the prefrontal cortex. No sustained activity in the posterior cortex. No panpsychism. Consciousness is an emergent property of specific brain architectures and does not exist at the fundamental level. The results of the adversarial collaboration were announced on June 23, 2023, at the Association for the Scientific Study of Consciousness meeting in New York. The full paper appeared in Nature in April of 2025. Neither theory won outright. But IIT fared better. 2 of IIT's 3 pre-registered predictions passed their statistical thresholds. None of global workspace theory's predictions did. Consciousness-related activity centered in the posterior cortex, not the prefrontal cortex, consistent with IIT, but sustained synchronization within the posterior cortex, another IIT prediction, was not found. That same day, in the same room, something else happened that received much less coverage but tells you more about the state of the field than any experimental result. In 1998, at a conference of the Association for the Scientific Study of Consciousness, in a smoky bar in Bremen, Germany, neuroscientist Christoph Koch had made a bet with philosopher David Chalmers. Koch bet a case of fine wine that the neural correlates of consciousness, the specific brain mechanisms that produce subjective experience, would be identified within 25 years. Koch was working with Francis Crick at the time, the co-discoverer of the structure of DNA, and the two of them believed that consciousness was a solvable problem, a problem of circuits and neurons and timing and feedback. Find the correlate and you have found the mechanism, and the hard problem dissolves. 25 years later, on that stage in New York, Chalmers declared, "It is clear that things are not clear." Koch conceded. He stalked off the stage and reappeared carrying a case of fine Portuguese wine. The audience laughed and applauded. And then Koch did something that should tell you everything about where this field is. He immediately doubled down. He made a new bet, extending the deadline to 2048, 25 more years. Chalmers took the bet. He said, "I hope I lose, but I suspect I will win." Koch had spent 20 years collaborating with Francis Crick, their last paper together, on the claustrum's role in consciousness. Edited by Crick on the day he died, July 2004, after Crick's death, Koch became the chief scientific officer of the Allen Institute for Brain Science, a $500 million research institution funded by Paul Allen with roughly 300 scientists. He had access to more data about the brain than any human being in history. And after all of it, He stood on a stage and admitted that consciousness had not been explained. The bet was lost. The hard problem remained. And that brings us to the theory that the scientific establishment has spent the longest time dismissing and that the evidence has most stubbornly refused to kill. In 1989, Roger Penrose published The Emperor's New Mind. Penrose had already won the respect of the entire physics community for his work on black holes, singularity theorems, and the mathematics of space-time. He would go on to win the Nobel Prize in Physics in 2020. And in that book, he argued something that made his colleagues deeply uncomfortable. He argued that consciousness is not computable, that the human mind does things that no algorithm, no matter how complex, can replicate. He grounded this in Gödel's incompleteness theorems, the mathematical proofs showing that any sufficiently powerful formal system contains truths it cannot prove within its own framework. Penrose argued that human mathematical understanding transcends formal systems, which means it transcends computation, which means consciousness must involve something that is not a computation. What kind of process is not a computation but is physical? Penrose proposed quantum gravity. Specifically, he proposed that quantum superpositions, states where particles exist in multiple configurations simultaneously, do not persist indefinitely. They self-collapse when the gravitational self-energy of the superposition reaches a certain threshold, a threshold set by the Planck scale, the smallest meaningful scale in physics. He called this objective reduction. It happens everywhere in the universe whenever a superposition becomes gravitationally significant. And he proposed that consciousness is what this process feels like from the inside. That was radical enough. But then he teamed up with Stuart Hameroff, an anesthesiologist at the University of Arizona, and the two of them identified a specific biological structure where quantum processes might occur inside neurons. Microtubules. These are cylindrical protein polymers that form the structural skeleton of every cell in your body, including neurons. They contain delocalized pi electrons that are spread across the molecular structure in a way that might support quantum effects. Hameroff and Penrose proposed that quantum computations happen inside microtubules, that these computations terminate via gravitational self-collapse, Penrose's objective reduction, and that this process, orchestrated by the biological architecture of the brain, produces consciousness. They called the theory orchestrated objective reduction, OR. The mainstream reaction was brutal. Patricia Churchland, one of the most prominent philosophers of neuroscience, dismissed it as pixie dust in the synapses. Max Tegmark at MIT published a calculation claiming that decoherence times in the warm, wet environment of the brain would be on the order of 10 to the minus 13 seconds, 13 orders of magnitude too fast for any quantum process to persist long enough to matter. The consensus was that OR was elegant, imaginative, and dead on arrival. But the experiments did not cooperate with the consensus. In 2203, a team led by Aristide Kaura published in ACS Central Science showing that tryptophan fluorescence propagates through tubulin via quantum exciton mechanisms, and that anesthetic gases dampen these quantum effects by up to 20%. In 2024, Travis Babcock and colleagues reported direct evidence of quantum superradiance from microtubules at room temperature, a phenomenon that should not occur if Tegmark's decoherence calculations were correct. And also, in 2024, a team at Wellesley College, led by Shahir Khan, published in eNeuro showing that rats given epithelion B, a drug that stabilizes microtubules, took over 1 minute longer to fall unconscious under anesthesia. More stable microtubules meant more resistance to unconsciousness. The correlation between microtubule stability and consciousness was direct, measurable, and exactly what OR predicted. This does not prove OR is correct. The theory remains controversial, and the evidence is early. But the pattern should disturb you, because the theory that says consciousness is fundamental, that says it arises from quantum processes at the most basic level of physics, is the theory that keeps generating confirmed predictions. And the theories that say consciousness is a byproduct, an emergent accident of neural complexity, are the theories that just lost a 25-year bet and a $20 million adversarial collaboration. We tried to explain consciousness with physics. We have been trying for 93 years. And what happened, slowly, quietly, with almost nobody willing to say it plainly, is that the arrow reversed. We did not explain consciousness with physics. We ended up needing to explain physics with consciousness. And that reversal, that quiet inversion of everything we thought we knew about the relationship between mind and matter, is the thing that should keep you awake. Because it has implications that go far beyond neuroscience and far beyond quantum mechanics. It has implications for what you are, for what reality is, and for whether either of those questions has an answer that a human mind can hold. And the most recent experiments, the ones from 2020 and 2025, are the ones that physicists are least willing to discuss publicly, because those experiments do not just suggest that consciousness might be relevant to physics. They prove with mathematical certainty that at least one of the assumptions you have been making about reality your entire life is wrong. The question is, which one? And every answer is terrifying. In August of 2020, a team at Griffith University in Australia published a paper in Nature Physics that did something no experiment had done before. It did not just test quantum mechanics, it tested reality itself. And the result was a mathematical proof, not a suggestion, not a hint. A proof that three things you believe about the world cannot all be true at the same time. The paper was led by Bohm, working with Howard Wiseman and Eric Cavalcanti, and it derived a new class of inequalities that is strictly stronger than Bell's theorem. If you have followed anything about quantum physics in the last 40 years, you know that Bell's theorem is the most important result in the field. It proved that the universe is not locally realistic, that there are no hidden variables working behind the scenes to give particles their properties before measurement. Bell's theorem closed the door on the comfortable version of reality that Einstein wanted to be true. The Bohm experiment closed a door that most physicists did not even know was still open. They called their result the local friendliness inequality. It is based on three assumptions. The first is the absoluteness of observed events. This is the idea that when a measurement happens, it has a definite outcome that is a fact for everyone, not a perspective, a fact. The second is locality, no faster than light influences. The third is no superdeterminism. Your choices about what to measure are genuinely free, not secretly predetermined by the initial conditions of the universe. Those three assumptions sound obvious. They sound like the minimum you need to do science at all. And the Bohm team proved that they cannot all be true simultaneously. At least one must be wrong. The local friendliness inequality is violated by quantum mechanics, and unlike Bell inequalities, even theories that accept non-locality but preserve the absoluteness of observed events are ruled out. This is not about hidden variables anymore. This is about whether facts are facts. Think about what each option costs you. If you give up the absoluteness of observed events, then what happened in front of one observer is not necessarily what happened. Period. There are no universal facts. Reality is observer-dependent in the deepest possible sense. This is the option that cubism, relational quantum mechanics, and many worlds all choose. In different ways, if you give up locality, then influences travel faster than light, and the carefully constructed framework of relativistic physics, every experiment confirming special relativity for the last 120 years, has a problem. If you give up no superdeterminism, then your measurement choices are not free. They were determined at the Big Bang. Every experiment you have ever run, every decision you have ever made about how to test reality, was scripted in advance by the initial conditions of the universe. You have never made a free choice in your life, and neither has any physicist who ever tested quantum mechanics. Every option is a catastrophe. And the experiment won the 2023 Paul Ehrenfest Best Paper Award for Quantum Foundations, which means the community recognized its importance. But you did not hear about it on the news. You did not see it discussed on any mainstream science channel. It was published, recognized, and then the world kept spinning as if nothing had happened. Let me be specific about why this matters more than Bell's theorem, because the distinction is crucial and almost nobody discusses it. Bell's theorem proved that the universe is not locally realistic, but it left open the possibility that the universe is non-local and realistic, meaning things could still have definite properties independent of observation, as long as you accepted faster-than-light correlations. A lot of physicists were comfortable with that trade. You could keep the basic picture of an observer-independent reality at the cost of accepting some non-local spookiness. Unsettling, but livable. The Bohm result takes that escape route away. Even if you accept non-locality, even if you accept that influences travel instantaneously across the universe, you still cannot preserve the absoluteness of observed events unless you also accept superdeterminism, which is the assumption that every choice anyone has ever made was predetermined at the Big Bang. The Bohm experiment is strictly stronger than Bell's theorem because it closes doors that Bell left open. It narrows the options to a point where every surviving interpretation of quantum mechanics involves the observer in some fundamental, inescapable way. Many worlds says every outcome happens but cannot explain your specific experience. Cubism says outcomes are personal experiences of agents. Relational quantum mechanics says facts are relative to observers. Even Bohmian mechanics, Bohm's own pilot wave theory, survives only because it accepts radical non-locality while giving particles definite positions. But the Bohm result means even that is not enough if you want facts to be absolute. John Bell himself, decades earlier, had asked the question that the Bohm experiment finally answered. He wrote, "Was the wave function waiting to jump for thousands of millions of years until a single-celled living creature appeared? Or did it have to wait a little longer for some highly qualified measurer with a PhD?" He meant it as a reductio ad absurdum. He meant to show that the idea of consciousness playing a role in collapse was ridiculous. But the Bohm experiment proved something that would have troubled Bell deeply. The absurdity he pointed to, the idea that observed events are not absolute, is now the mathematically favored option. This paper did not come out of nowhere. It was the culmination of a theoretical program that began with Castlav Bruckner at the University of Vienna in 2015, when he proposed an extended version of the Wigner's friend scenario involving entanglement between two separate friend and Wigner pairs. Bruckner's 2018 paper, A No-Go Theorem for Observer-Independent Facts, published in Entropy, formally derived the contradiction. And in 2018, Daniela Frauchiger and Renato Renner at ETH Zurich published a paper in Nature Communications with a title that should have stopped the physics world in its tracks. Quantum theory cannot consistently describe the use of itself. What they showed is that four agents using quantum theory to reason about each other's results reach contradictory conclusions. Quantum mechanics, applied to observers who are themselves using quantum mechanics, generates logical paradoxes. Renner said afterward, when we look back at history, at moments like this, the solution often came from an unexpected direction. That unexpected direction has not arrived. The paradox stands. The Bohm experiment confirmed it experimentally, and the field has no consensus on which of the three foundational assumptions to abandon. I want you to sit with that for a moment, not the physics of it, the sociology of it. Because what I am about to show you is a pattern, and once you see it, You cannot unsee it. Since 1927, the physics community has been conducting surveys of its own members, trying to determine what physicists actually think about the foundations of their own theory. The results are astonishing for what they reveal about the state of the field. In 1997, Max Tegmark surveyed 48 physicists at a Quantum Foundations conference at the University of Maryland. Copenhagen got 27%. Many Worlds got 17%. Bohm got 8%. Tegmark himself called the survey highly informal and unscientific. But it was the first attempt to quantify what physicists believe about the most fundamental questions in their field. In 2011, Maximilian Schlosshauer, Johannes Koffler, and Anton Zeilinger surveyed 33 physicists at a conference in Traumkirchen, Austria. Copenhagen climbed to 42%. Information-based interpretations got 24%. Many Worlds got 18%. And on the specific question of whether the observer plays a distinguished physical role, such as wave function collapse by consciousness, 6% agreed. That is 2 people out of 33. In 2013, Travis Norson and Sarah Nelson gave the same questionnaire at a conference called Quantum Theory Without Observers in Bielefeld, Germany. The result was a complete inversion. De Broglie-Bohm got 63%. Objective collapse got 16%. Copenhagen got 4%. The same questions administered at a different conference produced completely opposite results. This should alarm you. It means the answers to the most fundamental questions in physics depend on which physicists you ask. Which is another way of saying that the answers do not exist. The name of the conference itself, Quantum Theory Without Observers, tells you everything about the selection bias. Physicists who attend a conference on removing observers from quantum theory prefer an interpretation without observers. Physicists who attend a conference organized by a Copenhagen sympathizer prefer Copenhagen. The surveys are not measuring what physicists believe, they are measuring which physicists showed up. In 2016, Sujeevan Sivasundaram and Katharina Nielsen sent the survey to over 1,200 physicists at 8 universities. 149 responded. Copenhagen got 39%. But the most striking number was this: 36% said they had no preferred interpretation at all. Over a third of working physicists have no position on what their own theory means. And in 2025, Nature published the largest survey ever conducted, with over 1,100 responses from more than 15,000 invitations. Copenhagen held at 36%. Information-based interpretations came in around 17%. Bohmian mechanics at 7%, and only 24% of physicists thought their favored interpretation was actually correct. Robert Speckens at the Perimeter Institute remarked that many Copenhagen advocates are just drinking the Kool-Aid of the Copenhagen philosophy without examining it. Here is what these surveys tell you, taken together. There is no consensus, there has never been a consensus, and the question at the center of it all, the question of what measurement means, the question of whether consciousness is involved, has been open since 1932 and shows no sign of closing. Now I need to tell you a story about what happens to people who ask this question publicly. Because the history of this field is not just a history of ideas, it is a history of suppression. David Mermin was told at Harvard, early in his career, that he would never get a PhD if he allowed himself to be distracted by such frivolities as foundational questions about quantum mechanics. He spent decades avoiding the topic in public, building an untouchable reputation in condensed matter physics, before finally coming out as a cubist late in his career. John Clauser, who would go on to win the Nobel Prize in Physics in 2022 for his experimental tests of Bell's theorem, described what he called a very powerful stigma attached to anyone who questioned the foundations of quantum mechanics. When he approached Richard Feynman to discuss his Bell test experiments, Feynman threw him out of his office. The greatest experimental physicist of the 20th century was ejected from the office of the greatest theoretical physicist of the 20th century for asking the wrong question. And then there is David Bohm. And Bohm's story is the one that reveals the pattern in its ugliest form. Bohm was a brilliant theoretical physicist at Berkeley in the 1940s. He had studied under Robert Oppenheimer. He had contributed to the Manhattan Project. And in 1942, as a young man in a country at war, he had briefly joined the Communist Party. They did nothing, Bohm later said, but talk about things of no significance. He left after a few months. It did not matter. In May of 1949, the House Un-American Activities Committee subpoenaed him. He invoked the Fifth Amendment. On December 4, 1949, he was arrested for contempt of Congress. He was acquitted at trial, but Princeton's president Harold Dodds refused to reinstate him. Einstein reportedly wanted Bohm as his assistant, but Oppenheimer, the man Bohm had studied under, the man whose atomic bomb project Bohm had contributed to, had secretly named Bohm as politically suspect. Oppenheimer opposed the idea and advised his former student to leave the country. Bohm left. He went to Brazil, then Israel, then Bristol, then Birkbeck College in London, where he spent the last 26 years of his career. And while he was in exile, in 1952, he published 2 papers that should have changed the direction of physics. Those papers presented what is now called the de Broglie-Bohm interpretation, or pilot wave theory. It is a fully deterministic version of quantum mechanics, in which particles always have definite positions, guided by a real physical wave. There is no collapse. There is no measurement problem. The wave function is a real thing in the world that pilots particles along definite trajectories. The observer has no special role. Consciousness is irrelevant. It was exactly the kind of theory that should have attracted attention. Einstein had been looking for something like it. The math worked. The predictions matched standard quantum mechanics exactly, and the response was silence. Oppenheimer organized a seminar at Princeton specifically to dismiss Bohm's work. The Copenhagen establishment treated pilot wave theory as a philosophical curiosity, a dead end, an embarrassment. For decades, it was barely mentioned in textbooks. When John Bell rediscovered Bohm's papers in the early 1960s, he was astonished. He later said that he felt that Bohm's ideas were being deliberately ignored and that the reasons given for the neglect were not honest. Consider what that means. A fully viable interpretation of quantum mechanics, one that eliminates the measurement problem, removes collapse, and makes consciousness irrelevant, existed since 1952. The physics community did not refute it. They did not find a flaw. They ignored it. For decades, because it did not fit the orthodoxy that had hardened around Copenhagen. Physicists did not abandon pilot wave theory because it was wrong. They abandoned it because it was inconvenient, because it required non-locality, and because the man who proposed it had been branded a political liability by the very establishment he was trying to serve. And here is the part that connects Bohm's story to everything we have been discussing. Pilot wave theory was supposed to be the escape route. It was supposed to show that you do not need consciousness in quantum mechanics. You do not even need indeterminacy. The universe is deterministic. Particles have positions, and the wave function is just a guiding field. Simple. Clean. No consciousness required. But it was not simple. Bohm's pilot wave is non-local. It responds instantaneously to events across the entire universe. Change something here, and the wave adjusts everywhere, instantly, regardless of distance. This bothered physicists even more than the consciousness problem. And so, rather than accept non-locality, the establishment dismissed Bohm and kept the measurement problem unsolved. The irony is that Bell's theorem, proved in 1964, showed that every interpretation of quantum mechanics, including Copenhagen, is non-local. The feature they rejected Bohm for turned out to be inescapable. It took until 2022, 60 years later, for the Nobel Committee to acknowledge the importance of the experimental tests that confirmed Bell's theorem. And by then, Bohm was 30 years dead. The last conversation David Bohm ever had took place on October 27, 1992. He was at Birkbeck College. He called his wife Saral. He said, "You know, it is tantalizing. I feel I am on the edge of something." Then he took a taxi home. By the time the taxi arrived, he was dead. Heart attack. He was 74 years old. On the edge of something. A man who had spent his life trying to understand the relationship between the observer and the observed, who had been exiled by his own country and ignored by his own profession, and who died reaching for a conclusion he could feel but not yet articulate. Bohm had spent decades in conversation with Jiddu Krishnamurti, the Indian philosopher, exploring the nature of consciousness from a direction that no physicist would have expected. His wife Saral found Krishnamurti's book The First and Last Freedom in a library in 1959, and Bohm was struck by one phrase in particular: "The observer is the observed." More than 30 recorded dialogues over 25 years, published in The Ending of Time and the Future of Humanity. A quantum physicist and a spiritual teacher, circling the same question from opposite sides. What is the relationship between the one who sees and the thing that is seen? Are they separate, or are they one process artificially divided by the structure of thought? What makes these dialogues extraordinary is that Bohm was not indulging in mysticism. He was pursuing the same question that had driven his physics. In pilot wave theory, the particle and the wave are not separate. The wave guides the particle rides the wave. They are aspects of one system. But the orthodoxy of physics treats the observer and the observed as fundamentally different kinds of things. The observer is classical, definite, standing outside the system. The observed is quantum, indefinite, governed by the Schrödinger equation. The Heisenberg cut, von Neumann's movable boundary, is the line between them. And the measurement problem exists precisely because nobody can say where that line belongs. Krishnamurti was saying something remarkably similar from a completely different tradition, that the separation between observer and observed is an illusion created by thought, that consciousness does not stand apart from the world it perceives, but is woven into it. Bohm spent 25 years exploring whether this insight from contemplative practice had a correlate in the structure of physics. He developed what he called the implicate order, a framework in which the deep structure of reality is not fragmented into separate objects and observers, but is a single, undivided wholeness from which the appearance of separation unfolds. The quantum world in Bohm's later formulation is not strange. It is the fundamental nature of reality. The classical world, the world of separate objects with definite properties, is the anomaly, the thing that needs to be explained. Bohm never resolved it, but the question he was asking is the same question that von Neumann formalized in 1932, the same question that Wigner made explicit in 1961, the same question that Wheeler reframed as the participatory universe, and the same question that the Bohm experiment proved cannot be avoided. And now I need to correct something that has been bothering you, probably for some time. Because if you know anything about quantum mechanics and consciousness, you have almost certainly encountered two claims that are repeated constantly across YouTube, Reddit, and popular science books. Both claims are wrong. And correcting them is essential to understanding why the real situation is so much worse than the popular version. The first claim is that Schrödinger's cat proves that things can be in two states at once, that the cat is simultaneously alive and dead until you open the box, and this demonstrates the strange magic of quantum mechanics. This is backwards. Erwin Schrödinger published his cat thought experiment in 1935 in a paper called The Present Situation in Quantum Mechanics, written in German as Die gegenwärtige Situation in der Quantenmechanik, published in the journal Naturwissenschaften. It was an attack. He was ridiculing the Copenhagen interpretation. He wrote, "One can even set up quite ridiculous cases," and argued that the scenario prevents us from so naively accepting as valid a blurred model for representing reality. Einstein endorsed the argument in a letter to Schrödinger. "Nobody really doubts," he wrote, "that the presence or absence of the cat is something independent of the act of observation." Schrödinger thought the idea of a cat being both alive and dead was absurd. He was not celebrating quantum weirdness. He was arguing that the interpretation must be wrong because it leads to absurd conclusions. Every popular science account that presents the cat as proof of superposition has the story exactly backwards. And here is why that matters for our discussion. Schrödinger's argument was in essence the same argument that Wigner would make 26 years later. If quantum mechanics applies to everything, then the chain of superposition extends from particle to detector to cat to human observer. Schrödinger was pointing at the same crack that von Neumann had found in the math 3 years earlier, the same crack that has been open ever since. He just thought the crack meant the theory was wrong, or at least wrongly interpreted. 90 years later, the theory has been confirmed to extraordinary precision, and the crack is still there. Schrödinger was right that the situation was ridiculous. He was wrong that it could be easily fixed. The second claim you need to discard is that the delayed choice quantum eraser experiment proves consciousness can retroactively change the past. There are dozens of YouTube videos making this claim. They are wrong. The experiment was published by Yoon-Ho Kim and colleagues in Physical Review Letters in 2000, and what it actually shows is considerably more subtle and considerably less mystical than the popular version. Here is what actually happens. Signal photons hit a detector called D0. The total pattern at D0, all the signal photons combined, never shows an interference pattern. It is always a featureless blob. You cannot see fringes by looking at D0 alone. The interference pattern only appears when you sort the D0 data after the fact by looking at which specific idler detector on the other side of the apparatus each photon's entangled partner was detected at. Subset R01 shows fringes. Subset R02 shows anti-fringes. They cancel perfectly. No information travels backward in time. The correlations are fully explained by standard quantum entanglement, the same kind of correlation that Bell's theorem deals with. As the physicist Ruth Kastner demonstrated, the observed correlations are fully accounted for by standard EPR correlations, and there is no necessary temporal non-locality. The reason I am correcting these misconceptions is not to debunk the consciousness connection, it is to make the real connection clearer. And I need to take that a step further, because there is another category of claims that muddies the water even more. And being honest about it is essential. If you search for consciousness and quantum mechanics, you will find Dean Radin's experiments at the Institute of Noetic Sciences, in which subjects allegedly affected a double-slit interference pattern by directing their attention towards the apparatus. Radin published results in 2012 in Physics Essays, claiming a statistically significant effect with a z-score of -4.36. The problem is that in 2019, a 10,000 trial replication was conducted, performed blindly by Radin himself, and it failed to confirm the original results. The replication, published by Wallachek and von Stilfried in Frontiers in Psychology, identified an unacceptably low true negative detection rate, suggesting the original significance was driven by false positives. The original paper was published in Physics Essays, which is a pay-to-publish journal with a low impact factor. This is not the same as the experiments we have been discussing, which appeared in Science Advances, Nature Physics, and physical review letters. You will also find the Global Consciousness Project, a network of roughly 60 to 70 random number generators scattered around the world, which claims to detect global consciousness events. The project claims a cumulative 7 sigma result across 500 events over 20 years. The most famous claim involves 9/11/2001. Dean Radin claimed 6,000 to 1 odds against chance for deviations during the attacks. But when Edwin May and James Spottiswoode conducted an independent analysis of the same data, they found no statistically significant change during the actual attacks. The apparent effect came from a deviation roughly 4 hours before the events. And as they noted, had the chosen time period been a few minutes shorter or 30 minutes longer, the data would have been consistent with mean chance. Peter Bansel's 2017 analysis in the journal Explore concluded that the data do not support the global consciousness proposal. I am telling you this because the real evidence for consciousness in physics does not need to be inflated with parapsychology. The von Neumann chain is real. The Wigner's friend paradox is real. The Proietti and Bohm experiments are real. The hard problem is real. The failure of decoherence to explain definite outcomes is real. The growing experimental support for OR is real. The 25-year bet being lost is real. The mathematical structure of quantum mechanics demanding a role for the observer is real. All of that is rigorous, peer-reviewed, and published in the best journals in the world. And it is far more unsettling than anything the popular version offers, because the popular version gives you magic, and the real version gives you a structural crisis in the foundations of physics that 93 years of genius have been unable to resolve. Now, there is something that the founders of quantum mechanics knew that got lost somewhere in the middle of the 20th century and is only now being recovered. Max Planck, the man who started quantum mechanics in the first place, the man whose name is on the constant, gave an interview to The Observer in London in 1931. He said, "I regard consciousness as fundamental. I regard matter as derivative from consciousness. We cannot get behind consciousness. This was not a mystic. This was not a New Age guru. This was the physicist who, more than any other single person, created the field. And he said, consciousness is fundamental. Matter comes from consciousness, not the other way around." André Linde, a Stanford cosmologist and one of the co-originators of inflationary theory, the theory of how the universe expanded in its first fraction of a second, has said, "I cannot imagine a consistent theory of everything that ignores consciousness. In the absence of observers, our universe is dead." Freeman Dyson, one of the great theoretical physicists of the second half of the 20th century, said, "Mind, as manifested by the capacity to make choices, is to some extent inherent in every electron." And in 2025, Adrian Kent at Cambridge, a serious mathematical physicist, published a paper in the Philosophical Transactions of the Royal Society in which he stated, "I also think a truly unified and complete description of nature will include consciousness as a fundamental natural phenomenon." He published his personal credences, a formal accounting of how likely he considers various positions, and they showed quite high credence in stances that suggest new physics associated with consciousness. Then he added, "Many thoughtful physicists differ." That last phrase is doing a lot of work. It means he knows colleagues who agree with him. He is telling you they exist. He is not naming them. This is the pattern. The founders of quantum mechanics talked about consciousness openly. Then, in the post-war era, the culture shifted. Shut up and calculate became the unofficial motto of physics. Asking what the equations meant was treated as philosophy, which in physics departments is a word used the way other people use the word disease. Careers were destroyed, Bohm exiled, Everett driven out, Clauser rejected, Mermin silenced. An entire generation of physicists was trained to never ask the question that von Neumann proved was the most important question in their field. The scale of this suppression is difficult to overstate. When John Clauser was planning his first Bell test experiment in the early 1970s, the experiment that would eventually help win him the Nobel Prize 50 years later, he could not find a senior physicist willing to support the work. He approached Feynman, who threw him out. He described the environment as one of active hostility toward anyone who took foundational questions seriously. Nature published an article in 2024 that summarized the error with devastating clarity. By suppressing questions they considered too philosophical, post-war physicists created an unquestioning orthodoxy that influences science to this day. This matters because suppression creates a survivorship bias in what the public hears. The physicists who get on television, who write the popular books, who run the YouTube channels, are overwhelmingly the ones who stayed within the orthodoxy. The ones who had uncomfortable thoughts about consciousness and measurement either never published those thoughts or published them only after achieving unassailable careers. David Mermin is the perfect example. He waited until he was one of the most respected condensed matter physicists in the world before declaring his allegiance to cubism, an interpretation that places the experiencing agent at the center of physics. He could afford to say it by then. A graduate student could not. And here is the deeper problem. When you suppress a question for decades, you do not just lose the answers. You lose the culture of asking. You lose the training, the funding pipelines, the institutional infrastructure that would have developed if the question had been pursued openly. The 2025 Nature survey of over 1,100 physicists found that 36% had no preferred interpretation of quantum mechanics. Over a third of working physicists have not thought carefully about what their own theory means. That is not because the question is unimportant. It is because the culture told them not to ask. And then, slowly, beginning in the 1990s and accelerating through the 2000s, the question came back. The 2022 Nobel Prize to Clauser, Aspect and Zeilinger for their Bell test experiments was symbolic. It validated the foundational work that had been dismissed for decades. Oxford University Press published a volume in 2022 called Consciousness and Quantum Mechanics, with 17 chapters by prominent physicists and philosophers including Chalmers, Kent, Goff, and Penrose. A review in the British Journal for the Philosophy of Science noted that for many years any mention of consciousness in the context of quantum physics was generally restricted to New Age bookshelves, but recently consciousness has begun to tiptoe back into the limelight. The Templeton Foundation is now pouring millions into the question. $2.43 million to Chapman University in 2024 for a project called Agency in Quantum Observers. $20 million for the adversarial collaboration on consciousness theories, multi-million-dollar grants to the QSISS Consortium, and other foundational physics programs. The money follows the evidence, and the evidence keeps pointing in the same direction. But I need to be honest about something here, because honesty is what separates this from the New Age version of this story, and I refuse to sacrifice it for a more dramatic narrative. The hard survey data shows consciousness-based interpretations of quantum mechanics at 6% or below when explicitly listed as an option. That is not a majority. That is not even a significant minority. The stronger claim, the one I can defend with evidence, is not that there is a hidden army of consciousness-believing physicists too afraid to speak. The stronger claim is that the question has been systematically suppressed for 70 years. And that the suppression has begun to lift, and that every time a new experiment is run, every time the question is tested in a laboratory, the results come back consistent with the idea that the observer cannot be removed from the picture. The data from surveys and the data from experiments are telling you different things. The surveys reflect the culture, the experiments reflect the physics, and the physics is winning. But here is the thing about all of this. Every experiment, every survey, every biographical tragedy, Every institutional suppression and quiet rehabilitation is a thread, and I have been laying these threads out one by one, hoping you would see where they converge. Because they do converge. All of them. On a single point. And that point is the thing that nobody in physics wants to say plainly. Even now, even after the experiments are published, and the proofs are complete, and the bets are lost, and the money is flowing. The convergence is this. You cannot describe reality without reference to something that experiences it. Might not be able to. Cannot. Every path through modern physics arrives at this conclusion, and each path arrives independently from a different starting point, using different assumptions. And they all end up in the same place. I need you to understand how unusual this is. In physics, when independent lines of evidence converge on a single conclusion, that convergence is treated as strong confirmation. When general relativity and quantum field theory both predict that black holes radiate, physicists take that seriously even though the two frameworks are otherwise incompatible. When multiple independent measurements of the cosmic microwave background all give the same temperature to 5 decimal places, that is treated as proof. Convergence from independent sources is the gold standard of evidence in physics. And what you have here is convergence from at least 10 independent sources, not 10 experiments measuring the same thing, 10 completely different theoretical frameworks built on different assumptions by different decades, arriving at the same wall. I need you to understand how unusual this is. In science, convergence from independent lines of evidence is the strongest form of confirmation there is. When Darwin's observations of finches, Mendel's experiments with peas, and Watson and Crick's X-ray crystallography all pointed to the same underlying mechanism of heredity, that convergence was what made evolution undeniable. When measurements of the cosmic microwave background, the redshift of distant galaxies, and the abundance of light elements all pointed to the Big Bang, that convergence was what made the theory bulletproof. What is happening in the foundations of physics right now has that same structure. Multiple independent lines of investigation, using different methods, starting from different assumptions, involving different communities of researchers who in many cases are not talking to each other, are all arriving at the same conclusion. And the conclusion is one that nobody wanted to arrive at. Von Neumann's chain proves the formalism permits consciousness as the collapse boundary. Wigner's friend shows that removing consciousness leads to contradictory descriptions of reality. Decoherence explains the appearance of collapse but not collapse itself, leaving the question open. Many worlds removes collapse but cannot explain why you experience one branch, which is a question about consciousness. Wheeler's participatory universe makes observation, acts of registering information, the mechanism by which reality comes into existence. Cubism dissolves the measurement problem by making quantum mechanics about the beliefs and experiences of agents, placing the experiencing subject at the center. The Proietti experiment confirmed at 5 sigma that observer-independent facts may not exist. The Bohm experiment proved that at least one of 3 fundamental assumptions about reality must be abandoned, and 2 of the 3 options involve the observer. IIT derives from mathematical axioms that consciousness is integrated information, which implies panpsychism, which implies consciousness is everywhere, at every scale. The hard problem shows that physics cannot explain consciousness by its very structure, because structure and dynamics adds up only to more structure and dynamics, never to experience. And Penrose and Hameroff's ORC-00, the theory that was supposed to be dead on arrival, keeps generating confirmed predictions from quantum processes in the biological substrate of consciousness itself. None of these researchers set out to prove that consciousness is central to physics. Von Neumann was trying to formalize quantum mechanics. Everett was trying to eliminate consciousness. Wheeler was trying to understand information. Fuchs was trying to make sense of probability. Tononi was trying to measure consciousness, not connect it to physics. Chalmers was trying to solve philosophy of mind. The fact that they all ended up in the same place, pointing at the same wall, despite starting from different rooms, is not a coincidence. It is a convergence, and it demands an explanation that the field does not have. These are not different conversations. They are the same conversation happening simultaneously across multiple fields, approached from different angles by people who in many cases do not talk to each other. And they are all pointing at the same wall. The wall is this: consciousness is the one thing physics cannot explain. It cannot be derived from the physical. It cannot be measured directly. It cannot be reduced to computation. It does not have a universally accepted definition. There is no mathematical formalism for it. There is no unit of measurement. There is no instrument that detects it. And this thing that science cannot define, cannot formalize, cannot measure, and cannot explain, is the thing that physics increasingly says reality depends on. That is the terrifying part. Not that consciousness creates reality. You can debate that claim. Interpretations differ. Reasonable physicists disagree about the mechanism. But what you cannot debate, what the experiments and the theorems and the 93 years of failure have established, beyond any serious doubt, is that consciousness cannot be removed from the picture. It is not optional. It is not a philosophical curiosity. It is not a question for after the real work is done. Philip Goff, the philosopher at Durham University, argues in his book Galileo's Error that Galileo inaugurated modern science by stripping qualitative properties, colors, sounds, tastes, smells, the felt qualities of experience, from the physical world. Physics, since Galileo describes only structure and dynamics, what things do, how they move, how they interact, never what they are intrinsically, never what anything feels like from the inside. That was a deliberate choice, made 400 years ago, and it made physics spectacularly successful. But it also means that consciousness, the felt quality of experience, was excluded from physics at the very beginning. Not because it does not exist, because Galileo decided to leave it out. Think about what that means for the project of explaining consciousness with physics. You are trying to use a framework that was specifically designed to exclude subjective experience to explain subjective experience. The tool was built to ignore the very thing you now need it to detect. This is not an accident. This is not an oversight. This is the foundational architecture of modern science, and it was constructed this way on purpose because stripping out the subjective made the objective measurable. Galileo's trade was brilliant. It gave us 400 years of progress, but it also guaranteed that when physics eventually hit a wall that required consciousness to break through, it would have no tools to do so. And that wall is where we are now. And now, 4 centuries later, physics has circled back to the thing it excluded. The equations demand it. The experiments confirm it. The foundational crisis will not resolve until it is addressed. And the tool that physics built to understand the universe, the tool of structure and dynamics and mathematical formalism, is structurally incapable of handling it. It is like trying to weigh something with a ruler. The instrument was not designed for the measurement, and we do not have a better instrument. Galen Strawson at the University of Texas published a paper in 2006 in the Journal of Consciousness Studies called Realistic Monism, in which he argued that physicalism itself entails panpsychism. His reasoning was simple and devastating. Either consciousness emerges from wholly non-experiential matter, which would require what he calls brute emergence, something coming from nothing, a miracle dressed in scientific language, or consciousness is already present at the fundamental level. If you are a physicalist, if you believe everything is physical, then consciousness is physical. which means matter has experiential properties, which means panpsychism. Lee Smolin, one of the founders of loop quantum gravity and a physicist at the Perimeter Institute, who has challenged the establishment on multiple fronts, has described himself as a naive panpsychist since college. In a 2020 paper called The Place of Qualia in a Relational Universe, he proposed what he calls restricted panpsychism, a version in which consciousness is associated with specific physical structures, but is fundamental, not emergent. Christoph Koch, the man who lost the bet to Chalmers, the man who ran the Allen Institute's $500 million brain science program, has called himself a panpsychist. The neuroscientist, who had more data about the brain than anyone in history, looked at the evidence and concluded that consciousness is not something brains generate. It is something the universe has. Giulio Tononi's IIT predicts the same thing, derived from mathematics. Any system with integrated information above zero has some degree of experience, a photodiode, a logic gate, an atom. This is not philosophy. This is a prediction of the most rigorous theory of consciousness ever proposed, the theory whose predictions partially survived a $20 million adversarial collaboration while its competitors' predictions failed. And here is where the combination problem enters. And it is worth confronting honestly because it is the strongest objection to panpsychism. If electrons have some rudimentary form of experience, how do those micro-experiences combine into the unified consciousness of a human mind? How do billions of tiny experiential sparks fuse into the rich, streaming three-dimensional movie that is your awareness right now? This is called the combination problem, and it is real. Goff calls it the serious challenge for the panpsychist position and where the field is focusing its energies. Hedda Hasselmorch at the University of Inland Norway has proposed that mental combination works as a causal process culminating in fusion, the way droplets merge into a stream. But the details remain elusive. The honest accounting goes like this. Panpsychism has a problem. The combination problem. Nobody knows how micro-experiences combine into macro-consciousness. That is a genuine gap. A genuine difficulty. A place where the theory has not yet delivered. But here is what is rarely acknowledged. The combination problem is hard, but the emergence problem, the problem of explaining how consciousness arises from matter that has no experiential properties at all, is not just hard, it is structurally impossible within the current framework of physics. Because Chalmers is right, structure and dynamics adds up to more structure and dynamics. It does not add up to experience. You can describe every physical process in a brain at arbitrary precision. Every ion channel, every synapse, every neurotransmitter release, every electromagnetic field fluctuation, and you will have described a fantastically complex physical system. You will not have described why there is something it is like to be that system. You will not have explained the felt quality of blue, or the ache of loss, or the taste of coffee at 6 in the morning when the house is quiet and you are alone with your thoughts. Those qualities are not in the physics. They are not in the structure. They are not in the dynamics. And no amount of structure and dynamics, however elaborate, however precisely described, generates them. The combination problem may be unsolved, but the emergence problem appears to be unsolvable. Given a choice between a hard problem and an impossible one, the direction of inquiry seems clear. I have been building toward this for the entire time, and I think you can feel it now. Let me bring the threads together. Eugene Wigner, the boy from Budapest who walked home from school with von Neumann, who won the Nobel Prize, who published the paper that put consciousness into physics, spent the last decades of his life circling this question. He put consciousness in, then he took it out, swayed by decoherence calling his own earlier view solipsism. He went back and forth. In some later writings, he seemed to soften again, leaving the door open. And then he died in 2003 at the age of 99, having never resolved the question he raised. At 90, he wrote, "The full meaning of life, the collective meaning of all human desires, is fundamentally a mystery beyond our grasp." The man who formalized the consciousness problem in physics ended his life calling it a mystery beyond our grasp. His childhood friend von Neumann had opened the door in 1932. Wigner walked through it in 1961. Then he walked back, and the door stayed open behind him, swinging in a wind that has not stopped blowing since. John Archibald Wheeler, who coined black hole and wormhole and quantum foam in it from bit, who told his students, "The universe watches itself into existence," who drew a picture of the cosmos as a giant eye looking back at its own origin, regretted one thing in his later years. In 2006, 2 years before he died, he said, "How I wish that I had kept up the sessions with Everett." The questions that he brought up were important. Wheeler had let Everett go. He had watched his student leave physics and destroy himself, and he had done nothing to stop it because he was afraid of offending Bohr. Wheeler spent his life arguing that the observer creates reality, and the one observer he failed, the one he let slip away, was the man who tried harder than anyone to prove the observer does not matter. Wheeler died on April 13, 2008, at the age of 96. As a boy, he had touched an 11,000-volt power line to see what it would feel like. As an old man, he had touched the edge of an idea that was even more dangerous. His favorite maxim, the one he repeated to students throughout his career, was this: "If you have not found something strange during the day, it has not been much of a day." He found something strange. He found that reality might not exist without something to observe it. And instead of retreating from that strangeness, the way his profession expected, he spent his final decades building it into the most radical ontological proposal a mainstream physicist had ever seriously advanced. The universe as a self-excited circuit, a cosmos that brings itself into being through acts of observation. He knew how it sounded. He said it anyway. And when Feynman was once asked about Wheeler's later ideas, he replied, "Some people think Wheeler has gotten crazy in his later years, but he has always been crazy." David Bohm called his wife on October 27, 1992, and said, "I feel I am on the edge of something." And then he was gone. A physicist who had explored the observer and the observed with both a quantum physicist's rigor and a philosopher's depth, who had been exiled by his country and ignored by his field, died reaching for an insight he could sense but not yet hold. And somewhere in the archives of the world's physics departments, in the notes and the emails and the after-hours conversations that never make it into the journals, there are physicists who know that the measurement problem points toward consciousness, who know that decoherence does not solve it, who know that many worlds does not escape it, who have read the Proietti paper and the Bohm paper and the Frauschige-Renner paper, who have sat with Chalmers' zombie argument and felt its weight, who have looked at IIT and OR and the microtubule data and the 25-year bet and the $20 million collaboration, and who say nothing, because the culture of their field has spent 70 years telling them that asking this question is career suicide. That is changing, slowly, unevenly, with the kind of institutional reluctance that makes you want to scream. But the Templeton money is flowing. The Oxford University Press volumes are being published. The Nobel Committee recognized Bell's theorem experiments in 2022. Adrian Kent published his credences in 2025. The taboo is not weakening. The problem is getting worse. Because here is the thing that nobody is saying, the thing that everything in this 2 hours has been building toward. The problem is not that we cannot figure out whether consciousness is involved in physics. The experiments strongly suggest it is. The mathematical structure of the theory demands a role for the observer. The hard problem proves that consciousness cannot be derived from physics as currently formulated. All of that points in one direction. The problem is that we do not know what consciousness is. We are the foundation of our own theory of reality, and we do not understand what we are. Physics says the universe may require conscious observers, and the thing it requires, the thing it cannot do without, is the one thing we cannot define, cannot measure, cannot explain, and cannot even agree on whether it is fundamental or emergent, physical or non-physical, localized or universal. The foundation of reality rests on the one thing we understand least. That is not a gap in our knowledge, that is a crack in the floor of everything we have ever built. And you are standing on it right now. You have been standing on it your entire life. Every measurement you have ever made, every fact you have ever trusted, every moment of experience you have ever had, all of it resting on a foundation that physics says is essential and science says is inexplicable. Wigner saw this crack in 1961 and turned away. Wheeler saw it and drew a picture of the universe looking at itself. Everett saw it and split reality in half to avoid it, and it consumed him. Bohm saw it and spent his last decades in dialogue with a mystic, searching for the place where the observer and the observed become one. Chalmers named it and has been waiting 25 years for someone to solve it. Koch bet on it, lost and doubled down. Tononi tried to formalize it and ended up with Panpsychism. Penrose proposed quantum gravity. Fuchs proposed that physics is about what reality does to minds. Every one of them got closer. None of them arrived. And the reason none of them arrived may be the most unsettling implication of all. It is possible that consciousness is not the kind of thing that can be explained by a theory. Not because it is supernatural, not because it is beyond science, but because it is the thing doing the explaining. It is the lens through which every theory is constructed, every experiment is interpreted, every fact is registered. You cannot use the lens to see the lens. You cannot use consciousness to step outside consciousness and examine it from a neutral vantage point that does not itself require consciousness to occupy. This is not a philosophical trick. This is a structural feature of the situation. Von Neumann's chain does not terminate because there is nothing outside the chain to terminate it. The regress from particle to detector to computer to brain to mind does not stop because there is no view from nowhere. There is only the view from inside, and the view from inside is consciousness. The very thing we are trying to explain. Physics has been building a map of reality for 400 years. It is a spectacular map. It predicts the behavior of particles to 11 decimal places. It has given us nuclear energy, semiconductor chips, GPS satellites, and MRI machines. And at the very center of the map, at the place where all the roads converge, there is a blank space. No label, no explanation, no formalism of any kind. Just the thing that is doing the mapping. You are the blank space. And the question of what you are, the question that physics needs answered to complete its own foundations, the question that 93 years of the greatest minds in science have been unable to resolve, that question does not have an answer yet. It may not have an answer ever, not because the question is meaningless, but because the answer might require something that human science has never built. A theory in which the theorist is not separate from the theory. A physics in which the physicist is part of the physics. A description of reality in which the thing doing the describing is not outside the description looking in, but woven into its fabric, inseparable from the thing it describes. Bohm reached for this on his last day alive. Wheeler drew it on a chalkboard. Fuchs writes about it in a 2,300-page document he calls My Struggles with the Block Universe. Chalmers suspects the zombie argument points toward it. Tononi's mathematics may be circling it, and somewhere in the microtubules of your neurons, if Penrose and Hameroff are right, Quantum gravity is already performing the operation that gives rise to it, but nobody can say what it is. Nobody can write the equation. Nobody can build the instrument that measures it. And nobody knows if any human mind is capable of understanding a phenomenon that is, by definition, the human mind itself. There is a version of this story that ends with hope, with the idea that science will figure it out, that the next generation of experiments will crack it, that some brilliant young theorist will emerge from a university we have not heard of yet and build the bridge between mind and matter that everyone has been looking for. And maybe that will happen. Koch clearly believes it might, or he would not have doubled down on his bet with Chalmers for 2048. Chalmers and Kelvin McQueen published a paper in 2021 exploring how consciousness causes collapse might be rigorously tested using quantum computers. Koch himself is collaborating with Google Quantum AI on experiments involving xenon isotopes with different nuclear spins, testing whether the spin properties affect anesthetic effectiveness, which would be a direct prediction of quantum consciousness theories. The field is active, the experiments are running. But I am not going to tell you that story. Not because it is wrong, because it is incomplete. And the part it leaves out is the part you need to hear. Every previous crisis in physics was resolved by expanding the framework. Newton's gravity could not explain Mercury's orbit, so Einstein expanded the framework to general relativity. Classical mechanics could not explain black-body radiation, so Planck expanded the framework to quantum mechanics. Each time the solution came from the same direction: more physics, better equations, deeper mathematics, a bigger map. The consciousness problem may not work that way, because the thing that is missing from the map is not another phenomenon that can be described in the language of structure and dynamics. It is the precondition for that language to exist at all. It is the experience of understanding itself. And no amount of structure and dynamics, no matter how sophisticated, no matter how many Nobel laureates contribute, can generate experience from the outside. You can describe the complete physics of a sunset, every photon, every wavelength, every neural response in the visual cortex, and you will have left out the most obvious fact about it, which is what it looks like, what it feels like to see it. The felt quality of the red and the gold and the fading light. That gap between the physics of the sunset and the experience of the sunset is the same gap that opens up in von Neumann's chain. It is the same gap that Wigner's friend falls into. It is the same gap that Chalmers named and Koch bet on, and the Templeton Foundation threw $20 million at. It has not closed. It is not closing, and the experiments keep confirming that it matters. What we know is this: the experiments are confirmed, the theorems are proved, the measurement problem is open. The hard problem is unsolved. Consciousness cannot be removed from physics, and physics cannot explain consciousness. You have been told your entire life that science describes reality, that physics is the language of the universe, that the equations are the territory, not just the map. And what 93 years of foundational crisis have revealed is that this may not be true. The equations may be descriptions of what reality does to minds, and the minds, your mind, the thing reading this, the thing that just processed those words and felt something shift inside your understanding. That mind is the one thing the equations cannot capture. That is where we are. Standing on a crack, looking down, knowing the floor is not solid, and knowing that the thing we would need to fix it is the same thing we are standing on.